Let's get started. So today we are going to talk about piecewise functions, and kind of like the name would suggest, they are pieces of different functions kind of plopped together on one Frankenstein graph. So we'll read the words. We should read the words. Piecewise functions are pieces of different functions. Yeah, all graphed on the same plane. Let's consider the following example. So this function we're going to have is equal to x squared plus 1 when x is less than 2, and it's equal to 7 minus x when x is bigger than or equal to 2. So we're going to graph those pieces, and we're actually going to start by graphing each graph completely, and then we'll graph the pieces that we want. Now, in general, you don't have to graph each piece completely and then graph the pieces you want, but it's kind of nice to see the process. So, and I guess let's read the words as well. The graph of this function will look like x squared plus 1 to the left of x equals 2, and it's going to look like y equals 7 minus x to the right of x equals 2. So x squared plus 1, our usual parabola, except it's shifted which way? Up by 1. So instead of having the vertex at 0, 0, it's going to have the vertex at 0, 1. And it's going to look like, I guess I could try and plot points nicely, although I'm not super concerned about that really. It'll look like this. There's my parabola. And I personally kind of like to scribble on the part that I want. So I want the part of the parabola when x is less than 2. So here's the point 2, 5. And I want everything to the left of that. So I'm going to grab all of this and actually grab my piecewise graph. So all of that is the part I want. And I don't want anything over here. So I don't want any of this part here that I'm kind of circling. None of this. In a similar way, we can graph y equals 7 minus x. It's a straight line. I don't really think about like, so honestly, like when I'm graphing straight line, I don't think about like shifts and reflections and that stuff. I just think about it's a line. I'm going to find the intercepts and then draw the line through them. So this line would have a y-intercept of 7, an x-intercept of also 7, and then trying to draw the line through them. Drawing a straight line. There we go. There's our line y equals 7 minus x. Now, we only want the piece of this when x is bigger than or, when x is bigger than or equal to 2. So I'm going to start at x equal to 2, go up to the point 2, 5, and then I only want the part to the right. I want none of the part to the left. None of that. And then we're just going to take the two pieces that we want, or all the pieces that we want, and put them on the same graph. So I'm going to take this parabola. Oh, now I should point out, when you're doing this, it's a good idea to see what each function would equal at kind of the point of change. So we're changing from this first piece to the second piece when x is 2. So I should see what both of them are equal to when I plug them 2. Even though, and I will point out, this top function technically isn't defined when x is 2, right? This function is defined to be 7 minus x when x is equal to 2. It's still a good idea to see what both pieces are doing. So I plug in 2 to the bottom function, 7 minus 2 is 5. If I plug in 2 to the top piece of the function, 2 squared plus 1 is also 5. So these functions are going to meet up at the point 2, 5. Here's how I would graph it. So let's graph the parabola part first. And so I'm going to graph that. I guess I'll be super precise with my points. Oops, not precise enough though, because that shouldn't be the point there. It should be the point there. I'm blowing it, James. That should be this point here at -1, 2, and that point there. And this point. And then notice how I draw this. I'm going to graph the point 2, 5, but technically for the parabola, I don't quite have it yet. This is going to get an open circle. Let's really zoom in here so we can all see it very well. So, and you can ignore that point down there at -1, 1. It's not meant to be there. Bless you. In fact, I feel like I owe you kind of a beat now. So graphing the parabola. So there is the parabola y equal to x squared plus 1 when x is strictly less than 2. That's the first piece of my piecewise graph. Again, for those of you that might have just joined, we're looking at this graph of f of x equal to x squared plus 1 when x is less than 2, and equal to 7 minus x when x is bigger than or equal to 2. So here's the left piece when x is less than 2. And now we're going to graph the right piece. Now I'm going to show you here specifically when you graph the right piece, since this graph, this line does have the point 2, 5, we're exactly going to fill in that open circle and make it closed. And we're going to graph the rest of it. Use a ruler again, because I like using the ruler. So there's the right half of the graph. Y equal to 7 minus x when x is bigger than or equal to 2. Sorry, I think I see that. So that's the typical process for graphing a piecewise function. We graph each piece on the domain where it is defined. So this top piece, x squared plus 1, was defined when x was left or less than 2. This other piece, 7 minus x, was defined when x was bigger than or equal to 2, or to the right of 2. So I'm thinking of, here's my breakpoint at 2. To the right, we're getting the line. To the left, we're getting the parabola. Questions about this so far? It's okay to have questions. Like piecewise functions are always kind of funky because it's just like you can have a lot of pieces and you have to kind of be careful about how each piece is defined over what domain. So we might know what all the things look like, but we still have to be careful about which parts of them we're going to graph. Okay. We'll do some more examples, but really, if you have questions, don't hesitate to ask them. Now, I know there's only a couple examples on this handout. We're going to make up some more as we go along. So it's not just going to be these 3 examples. Then we'll no, we definitely got more examples to do than just these 3. Okay. So I will also mention, just because this is something you're going to see in future classes, I would point out that this function is a continuous function. And the way I would like you or encourage you to think of, not that we're not going to cover continuity in this class, not something we typically go over, but I would tell you just from a very easy definition point of view, you can tell if a function is continuous if you can graph it without lifting your pencil off the paper, your pen off the paper. So totally, if we were to graph this, right, I could have graphed it by starting here and graph. Oh, look, I don't have to lift my pen up. I mean, I did lift my pen off the paper, but I didn't have to, right? But I was trying to make it look nice. So. Right, but you can totally graph this one without lifting your pen off the paper. That is essentially the idea of continuity. There's definitely a more formal definition you will learn about in the first quarter of calculus, but that's not what we're here for. Okay, so let's look at the next example. Specifically, an example where the pieces of the graph don't match up nicely, or don't meet up, or line up, or whatever we're doing. Okay, so very similar graph to previously. Except now instead of x squared plus 1, we have x squared. But all the other piece is the same. So we're still going to have the first piece. I'm going to just draw the little pieces over here. So I'm going to have y equal to x squared, which just looks like my usual x squared graph. Now, I'm going to draw the whole thing. But we know that we only want the part up until x being just up to 2. So at the point which would be 2, 4, that's where we would stop. We would take everything to the left, right? That's where x is less than 2. So everything to the left. All of this. And then the other piece is the same as before. So I'm just going to say 7 minus x, like that. 0, 7, 7, 0. And at 2, if we plug in 2, we would get 5. That's the point 2, 5. And now we want everything to the right of 2. We want everything x greater than or equal to 2. We want everything to the right of this point that's on the graph. Oops, sorry. Do let me know if you can't see things. I know I often get not centered quite nicely, so try to keep things in view. So same idea. We're just picking the pieces that we want or need or told that we should have, and then we're going to put them on one graph. So now this graph is going to end at the point almost 2, 4. And again, I'm going to point out, you don't actually get that point, right? Because we're going right up until x is just less than 2. We're not actually getting to 2. So we're going to have a hole at the point 2, 4. So trying to plot this somewhat decently. I'm going to draw a hole at 2, 4 right there. So here's my parabola that is defined to the left of 2. Looks pretty good. And then we're also going to draw the other half, the right side of this piecewise function, which is starting at the point 2, 5, and then going down to the right. Now, typically, wherever you switch from one piece to the next piece, usually it's a good idea to make sure that we know what that point is. We often label those points. So if I was graphing this, I would certainly label this point. If it wasn't clear, like if I didn't have a nice grid where I could see all the numbers, I would label this point up here as 2, 5. And I would also label this not point down here, not where you don't actually get a point, but it kind of has a hole there, not kind of does. I would label that as 2, 4. It's good for the reader to know what they are actually seeing. So definitely when you have a hole in a graph or kind of like the end of one piece and the beginning of the next piece, we typically label all of those points. Questions so far? Maybe I personally found this confusing when I learned it first. I was like, this is weird. I don't like this, but if you guys don't have questions. Just to kind of go along with the theme from the last one, this function I would point out is not continuous or is discontinuous. There is definitely a break in the function, which is kind of the prime way we see this continuity. Or you could say, I had to lift my pen off the paper to be able to draw this graph. So it's not continuous. All right. We got examples for days. So let's look at the next one. Ooh, 3 pieces. Then I've got x squared, x minus, I should say x squared when x is less than or equal to 0, x minus 1 when x is between 0 and 1, and natural log of x when x is bigger than or equal to 1. So I'm going to do this part slightly differently than I did the previous one. I'm going to draw each graph on the side over here, but I'm going to draw just the part I want. Or maybe I'll draw the part I don't want with dash. So for y equals x squared when x is less than or equal to 0, my usual parabola, and I'm only going to get the left side. When x is less than or equal to 0. It's exciting. Yeah. Happens sometimes, sorry. Happens to me all the time with my watch. It's stupid. And then just to point out, right, the other part of the graph would be the other side of the parabola. So there's the part that we don't want. Dash. And then for x minus 1, well, x minus 1 is a straight line. It's got a y-intercept of -1. It's got an x-intercept of +1. And I only want the part between 0 and 1. Specifically, actually, I should have drawn those as open circles because I don't actually want them. So the graph would be the line going through all of this, but I only want this piece between x being 0 and x being 1. So I only want this little segment down there. And then lastly, the natural log of x, which we talked about last time, has the usual logarithmic shape. But I only want the logarithmic graph, so when x is bigger than or equal to 1. So at 1, the natural log graph does equal 0. A natural log of 1 is 0, log base 2 of 1 is 0, log of any log base of 1 is equal to 0. Log base 3 of 1, log base 4 of 1, right? Because 3 to the 0th power is 1, 4 to the 0th power is 1. So this one would look like this. It's got this vertical asymptote over here, which we don't want that part. And then we're going to hit this point, and then we want everything to the right there. So just to point out, this section here is x bigger than or equal to 1. This section here is x between 0 and 1. And this section over here is x less than, I know you wrote them right. Is x less than 0. Now, what I should also say is, you don't have to draw all 3 of these graphs on their own, right? You could totally just say, well, okay, I know it's going to be this part of the square, so I'm going to draw that first. Usually when I do this, I do go from left to right, which don't have to. So I'm going to draw that piece of the piecewise function. So I'm going to go down like that. And I am going to fill in that circle because I want x to be less than or equal to 0. And if x is 0, plugging it in gets x 0 squared, which is also 0. And then I'm not going to fill in these endpoints. I'm going to get the point. I feel like this grid is not meant for my not delicate hands that are not excellent at graphing small things here. So we're going to get this open circle here to this open circle here. That little segment right there. And then finally, we're going to get this last piece here, which is the right side of the logarithmic graph. So we're going to plug in the point 1, 0, which is going to fill in that open circle there. And then we're just going to go off to the right. So here is what our resulting piecewise graph looks like, which we totally could have drawn just by drawing this here first, then drawing this here second, then drawing this here third. So what I'm trying to say, you don't have to draw all 3 of these. I don't need to draw all 3 of them, but you certainly are welcome to draw all the pieces separately if you want to first. It's totally fine to do so. It just takes more time, right? So it's up to you if what you want to do. Okay. So now, more examples. And we'll try and do this somewhat more efficiently. Well, I should see one. Let me double check one thing here. Give me a moment. Sorry. Forgot about one thing. I know the pages are blank. I just want to see one thing. Make sure. Okay, cool. So let's look at the next example I have decided on, which is one I just made up. So we're going to graph now. In fact, maybe I'm gonna have. We'll do this one. I think all of you should try this one on your own. So try graphing the following piecewise function. F of x is equal to x plus 3 when x is less than or equal to -1, x squared minus 1 when x is strictly larger than -1 and less than or equal to +2. And finally, the constant function 5 when x is bigger than 2. And just as a reminder, I know we haven't talked about graphing constant functions a whole lot, but what does the function y equal to 5 look like? What kind of line is that going to be? Yeah, thank you. Exactly. This kind of line, which is, what do we call that? Horizontal. Because why horizontal? Because it looks like the horizon. That's how I always think about it. I don't have a good thing for vertical. The horizontal, definitely horizon is, I'm always thinking horizon. I'm thinking horizontal. So go ahead and try and graph all this. You can graph the pieces separately, but you don't have to. But definitely graph those pieces and then try to put them all on one graph. You all at home too, definitely give this one a shot before we go over. I'll give you like 2 minutes. I think that's a decent amount of time. We'll see. I'll walk around and see. What I want. Good job. Yeah. I'm gonna grab some extra paper. Why do I not have extra paper? So, in 2 minutes, yeah, no more 2 minutes. All right, so let's take a look at all the pieces first. So y equals x plus 3, straight line. I'm going to plot the intercepts. Y-intercepts 1, 2, 3. X-intercept is -3, and then draw the line through them. Now we're going to be careful. Well, I'll say a couple words at the end here, but I just want to point out we only want the piece of this up until x is equal to -1. So we actually want to stop right there and get everything to the left. I prefer doing it. I don't love scribbling on it, but I do the whole thing, so it's too late. X squared minus 1 is a parabola shifted down. So it's going to look something like this. Oh, and I didn't say where, so I should be a little more precise here, right? We want this one when x is less than or equal to -1. So we want to be everything to the left of -1. And here, for this next one, we want this piece when x is between -1 and 2. Specifically, x is strictly greater than -1, but less than or equal to +2. So at -1, we plug in -1, we get -1 squared minus 1, which is 1 minus 1, which is 0. So at -1, we would get that point there, the point -1, 0. And then if we go to the right, all the way over to x equal to 2, we plug in 2, 4 minus 1 is 3. So let's say we're going to be going from the point -1, 0, and getting everything from there up until the point 2, 3. We're not actually going to get the point -1, 0. It's going to be an open point or a hole. And then finally, y equals 5 is just looking like the nice horizontal line that goes through the y-intercept at 0, 5. Well, it would if we had that point in there, right? But we don't, because we're starting at x being just bigger than 2. So we don't want the point 2, 5, but we do want everything to the right of it. So putting all of these pieces together, this part, and this part, let's see what we get. So let's see, I've got my line. So, I should label this point too. So this point here, if I plug in -1, I get -1 plus 3, which is 2. So that's the point -1, 2. So I'm thinking about having the point -1, 2. Right there, and then it's going to go through the point -3, 0. Oops, come on, it's going to look like that. So there's my piece where it's x plus 3 less than when x is less than or equal to -1. And then for the x squared minus 1 part, I want all of this. I'm going to start at -1, 0, but I don't actually get that point, so it's an open circle. It should look like an open circle. I didn't do a great job there. And then we're going to go down and then back up to the point 2, 3. Should be ending right about there. And although it's not totally necessary, it's probably worthwhile to also point out there's a y-intercept there, which is 0, -1. There's an x-intercept here of 1, 0. Okay, fine. There's a lot of intercepts. This point here is 2, 3. And then finally, we get this other part. Oh no, I'm gonna make these a little bit bigger here. Sorry, that's fine. So the last piece here starts at the point 2, 5, which is just straight above this point here, but 2 above it, and then goes to the right. So there's our piecewise function. Something worth noting about these piecewise functions. They are typically functions. No one's going to give you a piecewise thing, typically, that is not a function. Meaning, it should pass what's called the vertical line test. So anything that's a function, each x input should only give you one y output. So if I pick a value for x, I can plug it into one of these pieces, but not more than one of these pieces. That corresponds to passing the vertical line test, meaning any vertical line that we could draw should only pass through 1 point on your graph. So if you were to graph this thing, well, in fact, let me show you examples I've seen in the past, because I've definitely seen some things where people have made some small errors. So let me show you just, for example, if you were to graph this instead, virtually the same thing, but let's say I accidentally got, I really wanted that y-intercept on the line part. So maybe instead of, getting just up to here, I went all the way up to here. So I got 1, 2, 3, 1, 2, 3. Let's say I got all of that. And then I still have all the parabola piece I need. So from there to there. So open here, and then 1, 2, and then back up to there, closed. 2, 3. And then finally 2 above at this point here. And maybe I was not careful. Well, no, let's be more careful than that, James. Let's say I graph this. It's not a function. It fails the vertical line test. If I draw this vertical line right here, look, it's going through more than 1 point on the graph. And the issue with what I've done here is that I got too much of one of the pieces, right? What I've really drawn is I've drawn y equal to x plus 3, but I've drawn it when x is up to being less than or equal to 0, instead of being less than or equal to -1, which is how it was originally defined. So be careful. If you see your graph kind of overlapping other pieces of your graph, like if you kind of drop them all down onto each other, if they actually touch each other when you drop them down, that's a problem. It's not passing the vertical line. I don't really like drawing a vertical line. To me seems weird. I don't love it. But what I really kind of think about is like, if I just let this first graph here slide down this way, would it touch the second graph? Oh yeah. Whereas with our correct graph, if I let this piece slide down, it would almost touch the other piece, but it wouldn't actually touch it because there's a hole there. So they wouldn't touch if we slid them vertically up or down, which kind of neat. I've never actually thought about it that way before, but it's an interesting way of thinking about it. I've just mentioned. So whenever you're drawing these pieces, make sure they don't overlap in this way. Yeah. Let's do some more examples. Oh, actually, let's do my favorite example. It's actually it's a very basic function, but it's definitely an important one to be aware of because it's going to come all the time. So let's say we want to look at, say, we'll do 2. F of x equal to, I want you all to do this one on your own because I think it's good practice. Let's say it's equal to the function negative x, when x is less than 0, and it's equal to x when x is greater than or equal to 0. I want you all to graph these 2 pieces, and then you can graph them all on one thing or graph the pieces separately, whichever way you want to do it. Let's see here. After you're done graphing this, you might recognize it as something else we've already seen. So that's it. And it's always kind of hard with these less than things, right? Okay, the alligator, I mean, honestly, still to this day, you've probably heard, I have never, the alligator eats the bigger number, right? Like most of us have maybe heard that. If you haven't heard that, the alligator eats the bigger number. So if you're saying x is less than 0, which thing is bigger, x or 0? 0, because it's the bigger thing that the alligator is eating. So that means x has to be smaller than 0, meaning x has to be negative. Similarly here, if x is bigger than 0, well, the alligator is eating the bigger thing, so x is the bigger thing. So x has to be a number that's bigger than 0, like 1 or 2 or 3 or whatever. if we start graphing this, and I would just graph this in one piece or one go. So y equals negative x looks like a straight line with a slope of -1. So when I am less than 0, meaning I'm over here, where x is less than 0, I'm going to get the line y equals negative x, which is looking like this. But I don't have it right there, so I'm going to make an open circle. Although I know it's going to get filled in, but you know, it's good to be precise. And then on the right side, when x is larger than 0, larger than or equal to 0, we get the line y equals x, which is the line with a positive slope of 1. It goes just like that. And it starts at the origin. We fill that point in, and then it goes up and to the right. And this function certainly has another name, the absolute value function. But it's really, really, really important that you all are aware that the absolute value function is a piecewise function. So that when you see it later on, it's always defined as, or I mean, we don't always write it out this way, but it's always reasonable to say the absolute value of x is just x if x is already positive, and it's negative x if x is negative. Sorry, I didn't mean to draw that there. And what's kind of cool is it actually works for the absolute value of anything. Meaning, if you're taking the absolute value of a number, if that number is already positive, we just leave it alone, right? It was already positive, great. On the other hand, if that number happens to be negative, the way we turn it into a positive is by multiplying it by -1. So this is another example of a function we could graph. Let's say we wanted to graph the absolute value of x minus 2, which is going to shift to which way? I should write y equals, apologies. Shift to which way? To the right, to the right. So we know what the graph of this looks like. It's going to be 1, 2 to the right. So the vertex is going to move 2 to the right. So it's going to look like this. What I also want to do, just so you all can see it, is write it as a piecewise function, so you can really believe that it is, because we'll see in a second that it really is. So if we write this as a piecewise function, here's how you do it. This only works for, this is only true for absolute values, right? This is not true for other. So taking the absolute value of something, if the stuff inside is already positive, what do? Nothing. Leave it alone, right? So if the insides are positive, okay, so if the insides are positive, we leave it alone. We don't change anything. So we just get x minus 2 if x minus 2 is already positive. You can throw in the equals part wherever you want. I'm going to put it right there. And then on the other side, so if on the other side, if the insides are negative, so if x minus 2 is negative, then we need to take this thing that's negative and make it positive. And we make something that's negative positive by multiplying it by -1. Now I'm going to simplify this just a little bit so we can make it a little easier to see what we've really got. So this absolute value of x minus 2 as a piecewise function is, if I distribute the -1 here, I get -x plus 2. And if I isolate x in this inequality, I get x being less than positive 2. I'm just adding 2 to both sides. And then for the second part here, x minus 2 is just x minus 2. But if I isolate x again over here, I get if x is bigger than or equal to 2. And if we look back at our graph, it's really exactly what we've got. Right? Here's 2. So to the right, where x is bigger than or equal to 2, this line certainly is the line y equals x minus 2. It's got an x-intercept of 2, and it would, if you continued it on down to the left, have a y-intercept of -2. On the other side, this is where x is less than 2. And if we look at this piece of the graph here, that is definitely the line y equals -x plus 2. It's got a y-intercept of 2, it's got an x-intercept also of 2, as that line does. So it's kind of neat that these absolute value things always can be written as piecewise functions. And it's actually a very useful thing, especially it really comes back, I would say, when you get to like the second quarter of calculus, if you're trying to find the area under some absolute value curve, being able to break it up into pieces like this is kind of a necessary thing. So it is something that's actually used in the future, not just talking about it for the sake of talking about it. Not that I totally would, but I'm not. Okay, let's do one or two more examples. Yeah, we got so much time. This is always a very short section. We've got lots of time. We might, I don't want to jinx it. I was gonna say we might end early today, but now that I've said it, we probably won't. Let's do a couple more examples. So let's try this thing on for size. Oh, we should do one of those. Yeah, let me actually grab this other example instead. Cool. Let's do this one. Let's do f of x equal to it's equal to 3 if x is less than 4. Oh, thank you. Good call. X is less than 4. Oh, what's 4 is a jeez. Come on, James. Let's go less than 1. And then let's say it's equal to 5 when x is equal to 1. And then let's say it's equal to 9 minus x when x is bigger than 1, less than or equal to 4. And then finally, let's say we've got the square root of x minus 3 and x is bigger than 4. Whoops, and I forgot there's no comma there. Sorry, it's terrible. It's an x. Sorry, I know things look terrible there. Here is our many pieces piecewise function. Let's graph them all separately, even though you might not want to. I don't think you definitely don't need to, but I'm going to. So f of x equal to 3, not too terrible. So y equal to 3 just looks like the usual horizontal line. And yeah, and I'm going to try and do the whole dashed thing. So I want y equal to 3 when x is less than 1. So there's 1. I want everything to the left of 1, but then at 1, the rest of it I don't want. So there's the portion I want of y equals 3. Everything that is left of or less than x equal to 1. And then this next part, I actually really shouldn't spend time graphing because I'm only getting this value of 5 when x is equal to 1. So this part here specifically is going to mean you're just going to get the point 1, 5. Because the function's only equal to 5 when x happens to have a value of 1. So not very, I don't think we need to graph that. Or we could graph it like right here. Well, let's not. So then y equals 9 minus x, another straight line, not a horizontal line, but a straight line. That has a y-intercept of 9 and x-intercept of 9. It'll look vaguely like this. Oh, I didn't do the dashed line thing because I got too carried away. You would have these points, but we really want to start at 1. I really want to start at the point 1, 8. And then I want everything. Oh, and then I want to end at the point at 4. So I want to end at 4, which would be the point 4, 5. And I want this to be open and I want that to be closed. I want x to be bigger than 1 and less than or equal to 4. Okay. And then finally, we've got the square root graph, which has been shifted 3 to the right. So 1, 4. So the square root of x minus 3 is going to look like the graph that starts at the point 3, 0, and then goes to 4, 1, and then continues on. But I only want the point starting after 4. I really want this to be an open point here. And then everything to the right. I want x to be greater than 4. So those are the pieces of my graph. This horizontal piece, the straight line piece, this square root piece. And then of course, there's also the point 1, 5, which we'll throw in at the end. All right, so now we put it all together. I might not, yeah. So sure, let's start over here. 2, 3, 4, 5. 8. I don't really want to do all that, but I guess we can. So we've got this to the left up until 1. So we start at 1, 3 there. So there's your horizontal line, y equals 3 to the left. And it's ending at the point 1, 3, which I'm going to fill in the labels later because it's good. As I learned from my last graph, you don't want to write the label where you might actually have to draw a point after that. So I would say wait to label things until after you've drawn the graph. Then I want the point 1, 5, but just that one point. And then I want the graph here starting at 1, 8 and going down to 4, 5. But again, I get an open point at 1, 8. So there's my 1, 8. It's going over to the point 4, 5. There's that segment of the graph right there. And then finally, my square root graph starts at the point 4, 1, and then goes off to the right. Like that. Graph looks kind of funky, but I will point out it is a function. A funky function. Because it definitely passes the vertical line test. Any vertical line you could draw would only go through one point of this graph at the most. It would be exactly one point here because it's defined as vertical. Oh, and then I should label things. So this is the point 1, 3, the point 1, 5. This would have been the point 1, 8. I should say this would have been the point 1, 3. This is the point 4, 5, and this would be the point 4, 1. Cool. Okay. Yep. I knew I jinxed it as soon as I said it. All right. Happens. I want to just throw one more example at you. It's actually not really a piecewise function, but there's something else I want you to see because it does come up occasionally. So sometimes graphs have holes. And the reason a graph has a hole is often because it's kind of undefined just at one point, but it's defined at every other point around. So let me show you an example of this. This is a pretty not too terrible example. So let's look at function, and this is, that's fine. So let's say we've got the function f of x is equal to x cubed minus 2x squared over x minus 2, which I will mention is technically a rational function, which we'll be talking about in a couple classes. Okay, so let me ask all of you, show me on your fingers, write in the chat, at what value of x is this function definitely undefined? I was asking, show me on your fingers, just to give everyone else a chance to say it. But yeah, it's definitely 2, right? And I'm sure most of you are like, oh yeah, that's 2. But yes, it's 2. Now, what I want to point out specifically here is that if you plug in 2, you definitely get 2 minus 2 on the bottom, which is 0. But you also get 0 on top. Plugging 2 on top, you get 8 minus 8, which is 0. And a 0 over 0 type of undefinedness is very kind of special and important. It's something you're going to encounter in calculus a whole lot. It's what's called an indeterminate form, meaning you can kind of take on any value. It's also undefined, though, meaning it doesn't actually equal anything specifically. It just is going to be really, really close to something. So here's what I want you to see in this example. We can factor. So this function, f of x, well, we definitely know x can't equal 2. For sure, not allowed, no matter what we do after that. So even if you simplify a function, once you've identified its domain, it can't change. You can't be like, oh, this function has this domain, 2 is not allowed, and then later on be like, well, okay, 2 is fine now. Doesn't work that way. If 2 is out, it's out. Like kind of like with the natural log equation we've done before, right? When you have a logarithmic equation, sometimes you get an extraneous solution because it works in a later version of the thing, but it has to work in the original version. So 2 is no good. So, but let's look at what we've got here. So if I simplify this, I can factor out an x squared. I'm left with an x minus 2. And it is totally valid to divide x minus 2 by x minus 2 and say that as long as x isn't 2, x minus 2 divided by x minus 2 is 1. Totally true, right? If x isn't 2, like if x is 2.3 or if x is 5, 5 minus 2 divided by 5 minus 2 is what? 1, right? Because it's 3 over 3, which is 1. Or 7 minus 2 over 7 minus 2. Or 10 minus 2 over 10 minus 2. No matter what we pick for x, other than 2, the top thing minus divided by the bottom thing is the same thing divided by the same thing, so it's going to be 1. Now, I really, really, really have to stress again, 0 divided by 0, not 1. It could be 1 sometimes, but it could also be 1,000 or 1,000,000,000. And again, that's a thing really you'll talk about in calculus when you talk about limits. The idea here is that for any x not equal to 2, x minus 2 divided by x minus 2 is just going to equal 1. So this function is really equal to just the x squared function as long as x does not equal 2. We could even plot some points, right? If x is 1, y or f of x is going to be, well, if x is 1, now I'm going to do all the math, even though it's going to be kind of silly. If I plug in 1 here, 1 squared times 1 minus 2 divided by 1 minus 2, minus 2's cancel, and I just get 1 squared. Or if I plugged in 3 squared times 3 minus 2 over 3 minus 2 is just 3 squared. So no matter what value of x I pick, as long as it's not 2, I just end up getting x squared. So even if x is like, if x was something close to like 2.1, the 2.1 divided by minus 2 divided by the 2.1 minus 2, those cancel out, those divide to 1, and we're left with 2.1 squared, okay, which is not a great number, it's 4.41. The idea, what I want you to really see here is that no matter what value of x we pick that's close to 2, the y value is going to be close to 2 squared. So you could pick something, and I think I've actually written things down here. Nah, not really. So you pick like 1.9, 1.9 squared, and then you'll have 1.9 minus 2. Well, that's going to be 3.61. Or if you can pick something like 2.00001, these parts are going to cancel because it's not 0 divided by 0. And then you're going to get 2.0001 squared, which is something very close to 4. It's like 4. I should find. I got time. I got like a minute. Like now I'm running out of time, so I tried to do all the things. Okay. So 2.00001 squared. 0001. Let's see what we get. It's 4.00040001. I'm pretty close to 4. Because here's what I want you to see. This graph has a hole at the point 2, 4. Everywhere else, it's defined to equal x squared. So this graph looks like the following. Everywhere other than 2, it is totally defined. And it's just whatever x squared is. But at this point here, there's a hole. Not defined there. You can't plug into this function. So you get 0 divided by 0, which is that. So this is an idea that's going to come back in the future, in future classes. But I just wanted to point out that sometimes graphs have holes. And specifically, you have holes when you have a factor that cancels, and whatever factor that canceled, whatever would have made it 0, that's the x value where you're going to have it. It's not a huge deal, like it's not going to come up with a whole lot, pun intended, but it will come up occasionally. Pun wasn't actually intended. I didn't mean to say that, but I was like, oh, that's great. So yeah. All right, we ended a minute early. See, I told you we could end early.